In our third installment, part three, we want to take a look at the concept of match pairs. So it is still the hypothesis testing for the difference between two population means, but there's a slight difference where the samples that we have are referred to as dependent samples, or that we take a single sample of individuals and repeat an experiment with them. And so we refer to that as well using an expression called repeated measures. This is a very useful technique because what it does, it's a situation where if you want to determine if there's a difference between two factors, then you want to eliminate all of the possible other factors that influence the difference or the result. And you do that by simply controlling for those other factors. And by using the same individuals before and after, or in situation one and situation two, then you could match the results to an individual. So, for example, say I wanted to do to determine whether or not student actually learned a whole lot after, say, attending a workshop or participants in a particular business. I could take, say, a sample of participants, say 15 participants, and then actually ask them a number of questions ahead of time. So, pre-test. And then I turn around and then after the workshop, I ask them the same questions and see how they scored. Excuse me. So I see how they scored, and the difference between the pre-test and the post-test is an indication of the improvement in their knowledge. So I wouldn't just randomly subtract before and after scores. I would actually subtract the before and after scores for a particular individual. So I am matching the pair of results, the before and after results. I am matching that to a particular individual. And hence we refer to that as a match pairs problem. So what happens now is that if we take the differences between the before and after, then we will get a single sample of differences. And if on average the difference is positive, then we interpret that one way. Or if the difference is negative, then we interpret that another way. It all depends on how we take the difference. So, for example, if I'm expecting to see an increased score in the after test, so before and after, I expect to say if I take mean of before, mean of after, so I'm going to take mean after minus mean before, I expect to see a positive difference if I want the mean after to be larger than the mean before. So that we'll actually take a look at a specific example, all right? But that's what match pairs is all about. And it really boils down to a single sample problem in the end, which we've already done in chapter 9. So let's just see this particular example and see why it's a match pairs problem. So this is problem 24 in our workbook D, and you can take a look at that. So the Global Business Travel Association reported the domestic airfare for business travel for the current year and the previous year. So it actually provided current year, previous year. So like a before and after. Below is a sample of 12 flights with their domestic fares shown for both years. So notice 12 flights and their domestic fares shown for both years. Now remember, they are reporting, the association is reporting the 2 years, and somehow they believe that there might be an increase. So we have a sample of 12 flights for the before and after, and we have the values from before and after. So we have repeated measures. We are asked to formulate the hypotheses. So let me just change my screen here so you can see the complete question. Formulate the hypothesis and test for a significant increase in the mean domestic airfare for business travel for the 1 year period. So essentially, just to put it in a simpler language, is there evidence that the mean business fare has gone up, right? Has increased. So they ask you to test whether or not it has increased, and we're told to use a 5% level of significance. They want us to find the p-value, etc. What is our conclusion? AKA do a hypothesis test, all right? So let's actually set that up. And the data doesn't show all 12, But to get the 12 values, you would have needed to go to the textbook and find a data file called business travel. I'm going to make that data file available to you in it's an Excel file. I will put it on the P drive, not a P drive, sorry, we don't do this P drive. I'm going to put it in Brightspace and in Padlet, and then you could actually access the actual data file there. Okay, but for our purposes, I'll just sort of do the computation and give you what you need to follow the example. So I'm going to come from the new screen, and we want to formulate the hypothesis. Now remember that they are hypothesizing that the fares have increased. So I'm going to let one of them be the before and one be after. So I'm going to let one, excuse me, I'm going to let one so one will be before, and I'm going to let two be after. So basically, if I want to show an increase, I expect 2 minus 1 should be positive, right? So mu1 would be mean before, mean fare before, and mu2 mean fare current, right, or after. Okay, so we want to test that the mean fare has increased. So H1 hypotheses. So we will say HO, HA. The mean fare has increased versus the mean fares, a business class fare has not increased. So mean business class fare has increased versus mean fare has not increased. So if the mean fare has not increased, it means that the fare before is either the same or larger. Now, because I'm looking for an increase, I will actually subtract mu1 minus mu2 because I expect mu2 to be larger, right? So I'm going to say mu2 minus mu1. If I'm expecting an increase, that difference should be 0. But if there isn't an increase, mu2 minus mu1 is less than or equal to 0. So we have to just make sure we understand how the difference should actually sort of play out. So after is supposed to be higher than before if there's been an increase. So therefore mu2 minus mu1 should be a positive, and that's what I want to prove. So that's that. Now, because we want to deal with this as match pairs, what we will do is we will define mu d, and I should have done it up here. That means the mean of the differences to be mu2 minus mu1. Okay? So I'm going to define mu d, the mean of the difference, to be the difference between those. So that I would replace that with mu d is less than or equal to 0, mu d greater than or equal to 0. Okay? That's how I'll do it. Excellent. So that's our first part. Second part now is our test statistic. 2. Test statistic. The test statistic in this case, because it just boils down to a single sample problem, is T is equal to the sample mean, or the mean of the differences, of the sample differences, which we refer to as X bar D. The mean of the population of the differences would be mu D. And then there's the standard deviation divided by the square root of n. If you look at that, that is very similar to what we've done before. in chapter 9 when we just did a single sample problem, and we were testing for population mean, and sigma was unknown. It's the same idea here. The standard deviation of the differences, sigma d, is unknown for us. Sigma d, unknown, because we just have a sample data. So that's unknown, and so we would actually use the t-distribution. So that's our test statistic. So one of the things I want you to notice is that this problem, even though we're testing for the difference between two population means, our samples are not independent samples, they're dependent samples. So by subtracting before from after or after from before, whichever way you do it, you will just have a single sample of differences, not two separate samples, but a single sample of the differences. And therefore, it boils down to a single sample problem. All right? 3 is our, let me just make some space on the side. Oops. Okay, we're doing like that. So that's fine. I'm going to go to a new page. Step 3. So now with we want our decision rule. All right. So what is the decision rule? Let's see. So is this a one-tail test or two-tail test? But remember, we're trying to find evidence that the price has increased. I've deliberately defined the difference as mu after minus mu before. And so therefore, I should be able to, let's use green, look for evidence up here. So I will reject HO if we're in this region. And because it's a one-tail test, this is alpha completely, 0.05. All right. So our critical value, T critical, is T 0.05. And because our sample size is 12, it's 11 degrees of freedom. All right. It's 11 degrees of freedom. So let us figure out what that is. All right. So give me 1 second. Well, I'm going to try to pull up my T table here and tell you exactly what that is. We need our critical value. So our critical value, it turns out to be okay, let me pull up my T table for you to see. So we want 0.0511, right? So I'm going to switch over to Padlet. And here we go. I should have had that value already, but sometimes I like to do things in real time. So 11 degrees of freedom, and the area in the tail is 0.05. So it's 1.796 is what we're getting, 1.796. So this says 1.796. All right, that's our critical value. So if our t value is greater than or equal to 1.796, we'll reject the null hypothesis. Sorry, why am I writing it out now all of a sudden? We'll reject HO. Otherwise, we fail to reject HO. So that's step 3. Let's do 4. And this is where we're going to need some 4, the analysis. Now, to do the analysis, if we go back to the problem, what we have to do with this particular problem is we need to create this here, the difference. Let me see here, a separate column for the differences, and then we have to calculate the difference between these matched pairs, right? So for example, the first one is a difference of 30. Second one is 63, right? Third one is negative 42. The price actually went down. Fourth one is 10, 10, and so on. So we could repeat all of that, and then we would refer to those as the differences, DI, the differences, okay? So the X bar D, which is the sample mean of the differences, is just a matter of adding up those 12 values and dividing it by 12. So going back here, for our analysis, we would need X bar D, which is the sum of the differences over N. So you don't have all of the data in that diagram, but I do have all of the data. It turns out that it is 276 over 12, and that's equal to 23. All right? So that's X bar D. We also need the standard deviation of the differences. And you may remember that the standard deviation formula looks something like this. Sum of the x squareds, but instead of x we're using di, sum of the di squareds minus the sum of x all squared, but instead of x we're using sum of the di's, divide by n, and then we divide by n minus 1. That's our shortcut formula I gave you. And that will help us to find the standard deviation. So you need to take all of the differences and add them up to get the sum of the di's. And then we need to take all of the differences and square them to get the sum of the di squareds. When you compute SD, so right now actually going ahead and doing all of that, this will turn out to be 38.80. And you could get the information once you have all of the sum of the di's, the sum of the di squared, you could substitute in here and you could get that value. Now that we have the standard deviation, I have the sample mean, I could go ahead and compute the t value. So t is equal to, remember, x bar d minus mu sd over the square root of n. So what's my x bar d? It's 23. In the null hypothesis, mu d, is equal to 0. And then SD 38.80 over the square root of 12. That gives me a t value of 2.05. 2.05. Now, if you recall, our critical value is 1.796, so 2.05 is in fact larger. So we can say, so let's find our p-value first though. So what is the p-value? P-value is the probability, since it's a one-tailed test, we don't have to multiply by 2, of the t-value being greater than 2.05. If we look up the table and we look at the 11 degrees of freedom, so let me see if I could pull up the table for you again. If we look up the 11 degrees of freedom, okay. So under the 11 degrees of freedom, if I keep going after 1.796 to try to find 2.05, I run into 2.22, which means that the 2.05 is between the 1.796 and the 2.201. So since it is in between there, it means that my p-value is between 2.5% and 5%, or 0.025 and 0.05. So our p-value, turns out, is it is actually larger than 0.025 but smaller than 0.05. So we have to write it as an inequality. Okay, so now we have the p-value. Now we have our test statistic 2.05. We know what our critical value is, 1.796. So now what do we have left to do? Just a matter of do our step 5. And let's see if I could do it this way. I'll move this. I'm going to just move that over to here. And so step 5, decision, conclusion. So since 2.05 is greater than 1.796, we will reject the null hypothesis. So if we reject the null hypothesis, therefore we will support HA. So that is our decision, our conclusion. Our decision is to reject. Our conclusion is we have sufficient evidence that the mean business class, the mean business fare, mean domestic business fare has increased. All right? So since we reject the null hypothesis, we have a possibility of type 1 error. And the risk of type 1 error is the p-value, which we know is between 2.5% and 5%. All right? And that brings us to the end of part 3, which looks at match pairs. All right? So with a match pairs problem, essentially what you're trying to do is to identify a single set of participants for which you are repeating the experiment, and therefore you could match the results. They're connected, 2 results are connected to 1 participant before and after. So 12 flights, you have 2 fares, 1 in the previous year, 1 in the current year. Okay? You have a before and after test. Each individual gives you a score before and a score after. So those are examples of match pairs. All right. So now our final video, part 4, will look at proportion problems.